So, welcome back process modeling of casting processes. So we will start with the derivation of energy equation. So, the energy equation is derived from the first law of thermodynamics, which states that the rate of change of energy of a fluid particle is equal to the rate of heat addition to the fluid particle plus the rate of work done on the particle. So, rate of increase of energy of fluid particle is equal to net rate of heat added to fluid particle plus net rate of work done on the fluid particle. So, as before we will be deriving an equation for the rate of increase of energy of a fluid particle for a per unit volume, which is given by rho d dt, that is rho substantial derivative of energy. So, then work done by surface forces. So, the rate of work done on the fluid particle in the element by a surface force is equal to the product of the force and velocity component in the direction of the force. For example, the forces given by all act in the x direction. So, the work done by these forces is given as so rho u minus del x rho u delta x by 2 and minus tau x x into u. So, it is quite similar with the treatment we have done before, only so we are multiplying it with the u. So, if you just see it before like we have done this for the momentum equation. Yeah, if I go back and show you. Yeah, so it is the similar treatment that has been shown over here that we are doing here again for the derivation of the energy equation. Okay. So, then rho u minus del x rho u by del x delta x by 2 minus tau x x into u minus del x tau x x u delta x by 2 minus rho u plus del x rho u by del x into delta x by 2 plus tau x x u plus del x tau x x into u into delta x by 2 into del y del z. Okay. So, so here you can see that so this is the whole expression here. So, it should not be closed over here. So, there is a problem with the bracketing here. So, these two brackets please correct it. So, it starts from here and cancels here, and then plus minus tau y x into u minus tau y x u by del y into delta y by 2 plus tau y x u plus del y tau y x u into delta y by 2 and multiplied by del x del z delta x del z delta z plus minus tau z x into u minus del z tau z x into u into delta z by 2 plus tau z x into u plus del z tau z x u into delta z by 2 multiplied by delta x delta y. So, this is the expression we are getting, the net rate of work done by these surface forces acting in the x direction can be given by. So, this is what I was pointing to the treatment what we have discussed in case of momentum equation. So, it is quite similar in case of energy equation, only the term difference in term here is that u, that we are multiplying the the rate of work done by the surface forces what we have discussed in case of momentum equation derivation. So, that same expression we are multiplying by the velocity in the x direction, that is u. So, then the resultant expression is del x into u minus p plus tau x x plus del y u tau y x plus del z u tau z x into delta x delta y delta z. So, surface stress components in the y and z direction also do work on the fluid particle. So, a repetition of the above process gives the additional rates of work done on the fluid particle due to the work done by these surface forces. So, the resultant expression will be del x into v tau x y plus del y v into minus p plus tau y y plus del z v tau y z into delta x delta y delta z, and again similarly for the z direction it will be del x w tau x z plus del y w tau y z and plus del z into w minus p plus tau z z into delta x delta y delta z. So, this is the rate of work done by the surface forces along the x, y and z direction. So, then so you can quite effectively understand from this schematic shown over here. So, this is the So here why the I mean this is the sign it's showing that this is the heat input into the control volume, that is Qx for the x direction minus del Qx by del x into delta x by 2, and the rate of heat heat flux leaving the control volume in the x direction is shown here as Qx plus del Qx by del x into delta x by 2. So now I mean we have seen here. So this is the we have like we have introduced before, what is the rate of increase of energy of fluid particle is equal to net rate of heat added to the fluid particle plus net rate of work done on the fluid particle. So now we already know the net rate of work done over the fluid particle. So that we we can get it, we can so which is expressed over here as divergence rho u, and then plus this is the expression that is plus del x u tau x x by del x plus del y u tau x y by del y plus del z u tau x z by del z plus del x v tau y x by delta x plus del y v tau y y by delta y plus del z v tau y z by del z plus del x w tau x z by del x and del y w tau y z plus del z w tau z z. So this is the so the net rate of heat, this is what we calculated, this is the net this is the net rate of work done on fluid particle. So that component is this total term. Okay. And now we have to calculate the net rate of heat transfer to the fluid particle due to the heat flow in the x direction. So which can be given by the difference between the rate of heat input across phase W, that is west phase, and the rate of heat loss across the east phase. Okay. Yeah. So now it is the east phase is this one and west phase is this one. So then heat is exiting in the x direction, that is so this is what is written over here. So then it is so then what is the heat input minus heat exit. So here heat input through the west phase is Qx minus del Qx into delta x by 2 minus heat exiting from the east phase, that is Qx plus del Qx by del x into delta x by 2 multiplied by delta y delta z. So then if you see that these terms gets cancelled and then this becomes negative. So then it becomes minus del Qx by del x into so because there are two minus, so then it becomes whole. So then multiplied by delta x, delta y, delta z. Okay. Similarly, the net rates of heat transfer to the fluid due to heat flows in the y and z direction can be calculated as minus del q y by del y into delta x, delta y, delta z, and minus del q z by delta z into delta x, delta y, delta z. So then now we need to add these terms. So then the total rate of heat added to the fluid particle for unit volume due to heat flow across its boundaries is the sum of equations divided by the volume delta x, delta y, delta z. So now what we are doing? We are just doing the addition of these three quantities. Okay. So then the resultant expression is del q x by del x minus del q y by del y and minus del q z by del z. Okay. So because we are dividing it by delta x, delta y, delta z, that is the volume. So then with the resultant expression is coming like minus divergence q. So the Fourier's law of heat conduction relates the heat flux to the local temperature gradient. So as we know that Qx is equal to minus k dt dx, del t del x, Qy is equal to minus k del t del y, Qz is equal to minus k del t del z. So this can be written in the vector form as, so q is equal to minus k grad t. So then we know that the total rate of heat added to the fluid particle is equal to minus divergence q. So then we have to write that so then and q is equal to minus k grad t. So the minus minus it becomes plus. So then divergence k grad t. Okay, or divergence k grad t. So this is how you have to. So this is the heat total rate of heat added to the fluid particle. So now to get the energy expression. So, now energy equation, so thus far we have not defined the specific energy E of a fluid. So, often the energy of a fluid is defined as the sum of the internal thermal energy, that is I, kinetic energy is that is half u square plus v square plus w square, and gravitational potential energy. So, here we will take the latter view and include the effects of potential energy changes as a source term. As before, we define a source of energy, we define a source of energy E per unit, SE per unit volume. So, here this will be the subscript, okay, per unit volume per unit time. So, the conservation of energy of the fluid particle is ensured by equating the rate of change of energy of the fluid particle to the sum of the net force of work done on the fluid particle, the net rate of heat addition to the fluid, and the rate of increase of energy due to the source terms. So, the energy equation becomes, so as we have introduced earlier. So, why this term is coming. So, if I go back to the first slide of energy equation. So, then this is basically the rate of increase of energy of a fluid particle per unit volume, which is depicted here. So, this term is depicted here as rho into the substantial derivative of energy as a whole. So, ddt of E, so which becomes equal to the so then net rate of work done over the control volume. So, what we have already got as here, so that is divergence rho u plus this expression over here. So, then for the energy equation we have to, so then minus divergence rho u plus del x u tau x x by delta x, plus del y u tau x y plus del z u tau x z plus del x v tau y x plus del y v tau y y plus del z v tau y z plus del x w tau z x plus del y w tau z y plus del z w tau z z, plus that is now the total rate of heat input to the fluid particle, what we have already derived as a divergence k grad T. So, now you just need to add it with the total rate of work done to the fluid element, so then we have to add divergence k grad T, and this is the source term that is we have discussed over here. So, source of energy per unit volume per unit time. So, then the energy expression takes the following form. So, this is the energy expression of the energy, conservation of energy. This can be written like this. And now, once we have discussed about the derivation of the momentum equation and also the derivation of the energy equation, and so then let us discuss about how to solve the momentum equation. So, then as we have introduced earlier, so the x momentum equation is del x rho u plus del y rho v u is equal to del x mu del u del x plus del y mu del u del y minus del p del x plus s u, and y momentum equation is del x rho u v plus del y rho v v and is equal to del x mu del v del x plus del y mu del v del y minus del p del y plus s b, that is source term in the y direction, and the continuity equation is del x rho u plus del y rho v is equal to 0. So, if the flow is compressible, the continuity equation may be used as the transport equation for density, and the energy equation is the transport equation for temperature. The pressure may then be obtained from density and temperature by using the equation of state, that is P is equal to P function of density and temperature rho T, whereas that is not the case in case of incompressible flow. So, the finite volume method starts as well as with the discretization of the flow domain and of the relevant transport equation. So, first we need to decide where to store the velocities. So, it seems logical to define these at the same locations as the scalar variables such as pressure, temperature, etc. However, if velocities and pressures are both defined at the nodes of an ordinary control volume, a highly non-uniform pressure field can act like a uniform pressure field and in the discretized momentum equation. So, if the velocities are defined at the scalar grid nodes, the influence of pressure is not properly represented in the discretized momentum equations. A remedy to this problem is to use a staggered grid approach for velocity components. How we can do that, we will be discussing next. So, as mentioned earlier, if the pressure field is known, the discretization of velocity equations and the subsequent solution procedure is the same as that of a scalar equation. So, since the velocity grid is staggered, the new notation based on grid line and cell face numbering will be used. So, this is in figure. So, this is a typical staggered grid. The unbroken grid lines are numbered by means of capital letters, okay, that is capital I, capital J. In the x direction, the numbering is I minus 1, I minus 1, I minus 1 I, and then I plus 1. So, here you can see. So, in the x direction, so I mean it is not written over here, however, it has to be, I mean we can write it like this. So, I mean so it is I j. So, then this is I minus 1 j minus 1 it will be. So, here the I j is marked, and then here I mean from P to this point, that is I mean W, which is written here as W, it will be I minus 1 j, I minus 1 j. If I write it here, I capital I minus 1 j. So, it is in the x direction, and then I mean I plus 1 j. So, I plus 1 j will be this point. So, here it will be I plus 1 j. Okay. Similarly, I mean in the y direction you see it is I j. So, then here it will be I j minus 1, and simultaneously here it will be I j minus 2. Okay. So, I mean it is shown only for I j minus 1, but we can write here I j minus 2. Okay. So, similarly here it will be at the top I j plus 1. Okay. So, I mean so then this is how I mean we can treat. So, the dashed lines that construct the cell faces are denoted by lower case letters. So, these are basically so it is not dashed line, it is grid line here. So, we are talking about these lines, okay, which are passing through the center of the cells. You can see this is the center of this particular cell. So, then they, I mean there the lower case letters are shown, that is I mean so where you can see here it is I j. Okay. So, then at this point from here to here it will be I minus 1 into j, and here it will be I plus 1 into j, and from if you go top in the y direction, then it will be I j plus 1. If you go bottom, then at this point it will be I j minus 1, and here it will be I j minus 2. Okay. So, this is how I mean we can do the treatment over here, and I mean so I mean this is how, so here I j minus 1 and I j minus 2. So, then if we move ahead, so then we can see a subscript system based on this numbering allows us to define the locations of grid nodes and cell faces with precision. So, I mean scalar nodes located at the intersection of two grid lines are identified by two capital letters, that is point P in figure is denoted by I j, that is it is shown again over here, and the u velocities are stored in the east and west cell faces of a scalar control volume. So, then this is the I mean so then there are two grids. So, one grid is the thicker grid which is responsible for storing the values of pressure as well as temperature in the nodal points, whereas the velocity values are getting computed and in the separate grid, that is shown by the thinner lines, and the analogous I mean locations of the nodes are marked here by the smaller I mean smaller I j, whereas for the I mean scalar variables it is marked as a capital I j, like pressure, like temperature. Okay. So, then So then the u velocities are stored at the east and west cell faces of a so similar of a scalar control volume. So these are located at the intersection of a line defining a cell boundary and a grid and a grid line, and are therefore denoted by a combination of a lower case letter and a capital. So that is the W face. So that is the W face of the cell around point P, okay, is identified by I capital J. So I capital J, you can see that here there is a small letter. So it is, we need to consult here for the yeah. So you can, we have to show it from here. So then you are here it is I capital J. So P is I capital J. So here this I will be a small I basically, and then for the same reasons the storage locations for the V velocities are combinations of a capital and a lower case letter, that is the SS face, that is the south face is given by capital I small j. Okay. So capital I small j, and then so then we may use forward or backward staggered velocity grids. The uniform grids in the figure are backward staggered, since the I location for the u velocity u I j is at a distance of minus half del x u from the scalar node capital I j, that is P. Likewise, the j location for the v velocity v I j is minus delta minus half delta delta y v. Okay. So then so then expressed in the new coordinate system, the discretized u momentum equation for the velocity at location I j is given by the following expression. So that is expressed in the new coordinate system, the discretized u momentum equation for the velocity at location I j, that is p small I small j. Okay. So from here it is at the west face. So that is here it is small I into capital J. So here there is this notation need to be corrected. So it is small I capital J. Okay. So then here the velocity at location small I capital J is given by this Aij Aij. So this will be subscript Aij Uij. So Ai capital J Ui capital J. Okay. So this need to be corrected. So this is for this point small I capital J. So the so this is so then is equal to summation of A n b U n b minus P I j P I capital J. So again here it will be so it P I capital J. So for this point, okay. So here it needs to be corrected capital J P I P I capital J minus P I minus 1 capital J, okay, into delta V u plus S bar delta V u, and then so which is or A small I capital J U small I capital J. So so again this has to be the same like this. So it is coming from here, okay, is equal to summation of A n b U n b plus P I minus capital I minus 1 comma j. J is the capital J here. So it is not small j. So that is I minus 1 capital J. So it is basically for this I minus 1 capital J. Okay, please correct it, and then so P I minus 1 capital J minus P I j, that is capital I capital J, that means for this point, okay, into A I j A small I into capital J, okay, plus B I capital J. Okay. So that is the concept of staggered grid. Okay. So and so where delta V u is the volume of the U cell and B I j is equal to S bar delta V u is the momentum source term. Okay. So A I j is the east or west cell face. So here it will be even easier for you to understand. So here I will write, so this is the east, so this is the east face and this is the west face. Okay. So we centered around P. So this is west and this is east face. So we are focusing our calculation in these two faces. So here so then the pressure gradient, so the pressure gradient source term in has been discretized by means of a linear interpolation between the pressure nodes on the U control volume boundaries. Okay. So this is basically, so the U control volume, so then the control volume which is written in terms of U, so that we have to now show. So the in the new numbering system, the E, W, N and S Naviers involved in the summation A N B U N B, that is shown over here, A N B U N B. Okay. So so the you can see sorry, so yeah, involved in the summation are I minus 1 j, I minus 1 capital J, comma I plus 1 capital J, comma I capital J minus 1 and I capital J plus 1. So their locations and the prevailing velocities are shown in more detail in this figure, which is shown over here. Okay. So the values of coefficients A I j, A small I capital J and A n b may be calculated with any of the differentiating methods like upwind or hybrid or quick, okay, suitable for convection diffusion problems. So the coefficients contain combinations of the convective flux per unit mass F and the diffusive conductance capital D at U control volume cell faces. So applying the new notation system, we give the velocities, we give the values of F, that is the per unit mass flux, and D, that is the diffusive conductance for each of the faces, that is small e, small w, that is east, west, north and south. Okay. Yeah. So then of the U control volume. So now we can see for the U control volume, if we focus our attention here now, so sir F w, so here F w, that is F west face mass flux is equal to rho U w is equal to F I j F I j F I j capital small I capital J, that is the, so F I j minus plus F I minus 1 into j. Okay. So this is for F I j for this phase, this point, and then we are calculating in the west phase. So then U I minus 1 capital J. So here this point has to be there. So then it will be I minus 1 capital J. Okay. Yeah. So so then so here this point it will be U I this is small I and this is this is the capital J. So this is P point. So then this, please correct it, this should be capital J, U I capital J. Okay. So then so F w is equal to rho U w is equal to F I j plus F I minus 1 j. So for this point plus F mass conductor mass flow flux at this point, so then we can get the mass flux at the west face of the U control volume, which is equal to half rho I j plus so now we have focused our attention to F I capital J, that is here, right. So then from here we can get rho I j, so rho I capital J. So here this is the this is the point. So here this is small e, so here it is capital I capital J. Okay. And so then rho I j plus, here we know that small capital I minus 1 comma j. So then we are getting from here this expression. Okay. So then it is half bracket rho I j plus rho I minus 1 j, that is here. Okay. Plus by 2 divided by 2 into U I j, U I capital J. Okay. plus rho I minus 1 j, okay, because now we are calculating for f I minus 1 j. So, f small I minus 1 j, that is which is falling over here, okay. So, then that is somewhere here, which is not drawn here, but for you have to make you understand. So, yeah, it is like this. So, this is the point. So, then there it is basically u I small I minus 1 comma capital capital J. Yeah. So, then it is basically so then when we are evaluating for f I minus f small I minus 1 j. So, then we have to write, so the rho I capital I minus 1 j. So, which is at the west face capital Y minus 1 j plus I minus 1 here. So, then here it will be so here it will be this is the west face, and then this is the capital W, that is the for the scalar initial grid, not the u control volume. So, then it is here it is u I minus 1 j for this point, and for this point it is this is capital I minus 2 comma capital J. So, then rho I minus 1 j for f I minus 1 j, it can be expressed as rho I minus 1 j plus rho I minus 2 j divided by 2 into u I minus 1 j. So, for this point, okay. So, which is which is at the capital W. Capital W west face, okay. So, then similarly for the east face F E, that is the mass flow mass flux at the east face small e. So, F E is equal to rho u E is equal to F I plus 1 j, I plus 1 capital J, and so plus f small I capital J by 2, which becomes equal to half rho I capital I plus 1 capital J plus rho I j by 2 into u I plus 1 j plus rho I j plus rho I minus 1 j by 2 into u small I capital J. So, similarly for the south face F s is equal to F I j is plus F capital I minus 1 into small j by 2. So, which becomes equal to half rho capital I j plus rho capital I j minus 1 by 2 into V capital I small j plus rho I minus 1 capital J plus rho capital I minus 1 capital J minus 1 by 2 into V capital I minus 1 small j, okay. So, similarly for the north face it comes as F n is equal to rho V n is equal to F I F capital I j small j plus 1 plus F capital capital I minus 1 capital I minus 1 j plus 1. So, this needs to be corrected. So, here it should be F capital I minus 1 small j plus 1. So, this is so then this plus this divided by 2, okay. So, which is equal to half rho capital I capital J plus 1 plus rho capital I j by 2 into V capital I small j plus 1 plus rho capital I minus 1 comma capital J plus 1 plus rho capital I minus 1 capital J by 2 into small v capital I minus 1 comma small j plus 1, okay. So, then now we are we have to calculate. So, we have already calculated the that is this the convective flux per unit mass F. So, now we need to calculate the discretize the diffusive conductance in the grid point, that is capital D. So, where you can see that it is for west face for u control volume, that is small w is equal to del capital I minus 1 capital J by small x I minus x I minus 1, and east face the diffusive conductance capital D E is equal to del capital I capital J by x I plus 1 minus small x I. So, then and then for for S, that is for south face of the u control volume, So, because there are no immediate node is available, so then in this case it is the average is taken for the nearby 4 nodes. That means I mean del capital I minus 1 j. So, here we are taking average for this point, this point, this point and this point. Okay. So, this is how we are treating for this. So, then it is del capital I minus 1 j plus del capital I j plus del capital I minus 1 capital J minus 1 plus del capital I j minus 1 capital J minus 1 divided by 4 y capital J minus y capital J minus 1. And then for the north face of the U control volume, the diffusion conductance capital D n, again the similar treatment for the north face. Okay. So, which is marked here as small n. So, which is not shown at the top, but the similar treatment like the southern face. So, then d small n is equal to del capital I minus 1 comma capital J plus 1 point plus del capital I capital J plus 1 plus del capital I minus 1 comma capital J plus del capital I capital J divided by 4 y j plus 1 minus y j. So, then from this we are finally getting the expression for a I j v a I small j in v capital I small j is equal to summation of a n b v n b plus p capital I capital J minus 1 minus p capital I j into multiplied by a capital I small j plus b capital I small j. So, then so this is how we have already calculated this expression that is shown over here, that is a I j and u I j. Okay. So, now we have calculated that. So, so now we have to treat it. So, then solving for the so the Naviers involved in and so the coefficients. So, similar treatment we have to do for the y direction also. So, for the y direction the treatment is quite similar, and then in this case it will come as the similar way. If we derive, then finally we will come to the expression as for the y direction we will we will get the values of the this mass flux in the east, in the west, south, north and east faces, as well as diffusion conductance for the west, east, south and north faces, which is quite similar to the x direction of the momentum equation discretization. So, here only we have to do it for the V control volume. So, here so here there is a mistake over here. So, then this expression, so here it will be small u capital I j, that is what we have discussed earlier. Yes, a small I j, small u, small I capital J. Okay. Yeah. So, a capital I j, small u, small small u capital I small j, capital I small j, and here capital I small j. Yeah. So, here we have discussed. Yeah. If we go back to the expression, yeah, a I capital J, u small I capital J. So, this is basically, that is for the x momentum equation. So, that is the x momentum equation which comes for which we have calculated the values for the mass flux at the east, west, north and south faces, as well as diffusion conductance for east, west and north and south faces. And then for the y momentum equation, the expression will be a I capital A I capital small. So, it will be, if I write here, so it will be a small a capital I small j v capital I small j is equal to summation of a n b v n b plus pressure P at capital I capital J minus 1 minus P capital I J capital J into A capital I comma small j plus B capital I small j. So, this is the this is the discretized form of the y momentum equation, and for this if we have to we can follow the similar procedure to calculate the mass flux for west phase, for east phase, for south phase, for north phase, and the diffusion conductance for west phase, for east phase, south phase and north phase. So, this is how we can basically solve the momentum equation, x momentum as well as y momentum equation, and so for the simple algorithm we can follow the so this is the flow chart of a simple algorithm. So, where so the maybe we can discuss about the simple algorithm and its treatment procedure in the next class. So, we are stopping for this class here. So, we will meet soon with the simple algorithm. Thank you.